In this video, we are going to continue solving A-level chemistry paper 1, June 2021. But before we continue, I want to appreciate those of you who have taken your time to subscribe to our channel. But for those of you who haven't subscribed to our channel, I just want to remind you that we are not asking you to donate or to buy pamphlets. Our resources are free. We are more interested in your success. What we want from you is to subscribe to our channel, like our videos, and share to fellow learners. Thank you very much for taking your time to subscribe to our channel. Let's get started. Question number 28. 0.58 gram of a volatile organic liquid when vaporized at 25 degrees Celsius under 1 atmosphere occupied a volume of 0.24 dm cube. What is the molar volume of the liquid? The gas constant is 0.082 atmosphere dm cube per kilo per mole. Now, what you do with this type of question is that there are two methods. Either you do the conversion or you use the value and convert only a few of them. For instance, you have to use the ideal gas equation, which is PV equals to nRT. And here, the conversion you are going to do here is you have to convert the temperature to Kelvin, you have to convert the volume to m cube, and you have to convert the pressure. You have to convert the pressure to Pascal, and the gas constant. You have to also convert the gas constant. And converting to Kelvin, you have to add 273. And in converting to volume, if it is in cm cube, you divide it by 1 million to have m cube. If it is dm cube, you have been given by dm cube, you divide by 1,000. Then in Pascal, 1 Pascal here is 1 kilo, 1 atmosphere, sorry, atmosphere into Pascal. 1 atmosphere is 101,325 Pascal. That is what you are supposed to do. I say if you were given cm cube, to have m cube, because you have to convert the volume to m cube, you divide by 1,000. But if you were given by dm cube, you divide by 1,000. You have to divide by 1 million. If you were given in cm cube, you have to divide by 1,000 if your volume were given in dm cube, and you have to add 273. For what I've just done here, I said you have to use the ideal gas equation, PV equals to nRT, and in this case we are looking for the molar mass. We are looking for capital N, which is PV equals to a small m, that is the mass divided by the molar mass, or the N is a number of moles, gas constant times the temperature. We are making the m the subject, which is the molar mass. The molar mass here will be P will be mRT divided by PV, and you know P is pressure, D is volume. So I said the conversion, we need to convert. The mass has been given. We need to convert to Kelvin by adding 273. By adding 273, then since 1 atmosphere was given, we need to convert it to Pascal, and 1 atmosphere is equal to 10132 Pascal. The volume we're given by the dm, so we need to have it in m cube. So we need to divide by 0.24 dm cube by 1,000 to have 0.0024 m cube. Then the gas constant. The gas constant is given in the question. It is given in atmosphere dm cube per kilo per mole. But to have it, you have to change that to what? To joules per kilo per mole. And when you divide it by, when you multiply it by that, it will give you but 8.31. So it will be, the gas constant will, instead of 0.082, it will be 831. If you do that and you substitute your value, we will multiply the gas, the mass, which is 0.58, times the gas constant, which is 8.31, times 298 divided by the atmosphere. A pressure, which is 101325, and then times what? Times the we were times the volume that we have already divided, times the volume. So we are making this the subject PV and we are making M the subject MRT divided by PV. Divided by PV. Divided by PV. So we are dividing it by PV. So when we do that, that's the pressure times the volume. When we do that, we will have 59.006. Another method you can still do using this very conversion, another method is, since the gas constant, the ideal gas equation is PV equals to nRT, we will look for the number of moles. The number of moles will just be equals to PV divided by RT. When we look for the number of moles using these converted values, we will have 0.0098 moles. When we have this number of moles, remember that the molar mass is always equal to the mass divided by the number of moles. Since the mass was given and the number of moles have been calculated, what we will do is we will divide the mass, which is 0.58 that was given, divided by the number of moles that we have calculated, and we will see have 58.18. 58.18. That is there are two ways you can do that. But if you don't want to do this conversion, if you don't want to carry out this conversion in your calculation, you can still use your values. You can still use your values, but convert only the temperature. Convert only the temperature and the volume, and everything I think will be okay. I will prefer that you do the conversions, because this is what we are currently using. Do the conversions into the current standard, into Kelvin, into M cube, into Pascal, and convert the gas constant and follow the ideal gas equation. You will have it like that. When you do it, that is 59.06. 59.06 or 59.18. Let's see 59.06 and 59.58. What would be our answer here? Okay. Now our answer here will be what? Implying that the answer, after doing the calculation, we check on the answer column. Our answer here will be what? Our answer for question number 28 will be a B. After doing our calculations, you will see that after doing the calculation, doing the conversion using the two methods, you have the value 59.006. Then the other one is 59.18. Well, maybe calculation errors, some percentage errors that are there. So we will have that answer there, which is 59.05. It takes us to question number 29. Question number 29 is An organic compound was fused with metallic sodium. With metallic sodium, an organic compound was fused with metallic sodium, plunged in water, and the solution filtered. When a few drops of sodium nitroprusside were added to a portion of the filtrate in a test tube, a violet coloration was observed. This shows that the organic compound contains A. Potassium, B. Nitrogen, C. Sulfur, D. Halogen. Yes, I know it will be very, very confusing to you, but this is how you can get a solution to this. Here we say that a violet color with sodium nitroprusside is a test. Remember, a violet color with sodium nitroprusside is a test for the presence of sulfur in an organic compound. This is a test. You might not know, or maybe you haven't done that, but I am telling you that a violet color with sodium nitroprusside is a test for the presence of sulfur in an organic compound. Note, sodium fusion is converted into sodium sulfite. 2. The sulfide ions are then identified using sodium nitroprusside. This is how it goes. I said step 1. Step 1. Step 1. Na plus will give us Na2S. Step 2. Step 2. Na, we are taking this one. Na2S plus Na is a complex type of compound you would not know. Cn, that's cyanide. Sorry. Five. Gives Na five NOS. So as I said that a violet color. Let me go back to the question so that you can better understand. Question number 29. A violet color here, the violet color in this question here, a violet color with sodium nitroprusside is a test for the presence of sulfur in an organic compound. It should be noted that sodium fusion is converted to sodium sulfite. I've just written the equation. Sodium fusion is converted to sodium sulfite. The sulfide ions are then identified using sodium nitroprusside. So now sodium fusion is converted to sodium sulfide. This is the sodium fusion. The sodium fusion is now converted to sodium sulfite. Then the sulfide ion here, are then identified by using sodium nitroprusside. The sulfide ion in this compound here. The sulfide ion present here, the sulfide ion present here are then identified by using what? By using sodium nitroprusside. This is sodium nitroprusside. This is sodium nitroprusside here. So the sodium ion here, the sulfide ion the sulfide ion in sodium sulfide. This is sodium sulfide. The sulfide ion in sodium sulfide are then identified by using this compound, sodium nitroprusside. This compound is sodium nitroprusside. So our question here was that. Question number 9. This shows the organic compound contains what? It contains sulfur. Potassium. No. It contains nitrogen. No. It contains sulfur. Yes. Because I said initially, a violet color with sodium nitroprusside is a test for the presence of sulfur in an organic compound. So this shows that the organic compound contains sulfur. So C is our right answer. C is our right answer for question number 29. Question number 29, C is the right answer. Question number 30. Question number 30, we have a sample of 2.3 grams of ethanol was mixed with an excess of aqueous acidified potassium dichromate 6 and refluxed to give ethanoic acid. If the yield of product was 60%, what mass of product was collected? It's a simple proportion type of thing. Very, very simple as it is. A simple proportion type of thing as you look at it. Very, very simple as you look at it. So what is happening here is this is the sample. It was mixed. The process of doing this is a reflux. To obtain this is you have to go through, you hit through reflux. So, and acidified potassium dichromate. This is a strong oxidizing agent. And what is going to happen here? Since we are using ethanol, we are going to oxidize it to ethanoic acid. But our major important thing here is the mass that was given. The mass that was given. This is the theoretical mass. This is the theoretical mass that was given, or a theoretical mass that was given. And they calculated this is the theoretical mass, which is 2.3, and our actual mass, or the experimental mass, is what? The actual mass, or what we call actual yield, or what we also call experimental yield, is 60%. So what mass of the product was collected? They have already given us the percentage. It's just to convert it into mass. But remember, there is a formula that percentage yield is equal to actual yield. Another word for actual yield is experimental yield divided by the theoretical yield times 100. So now let's solve this in this way, so that you can better understand what is there. Let me see, can solve it here. Excuse me, let me solve it here for you. Okay, I have the formula here is we have CH3, we have CH3, CH2, CH2OH. It undergoes oxidation to produce CH3 CH uh, to produce CH3 COOH. Here, what has been done here is that is chromium acidified. Yes, it's acidified, and what is going there? What is undergoing there? There's oxidation that is taking place. Oxidation. And what are the masses? There we have two masses that are we have, this is 2.3 gram, and this is what? This is 60%. The product is 60%. 60%. Another equivalent for 60% is 0.6. That is 0.6. Now, 60%, that is 0.6. Now, what we are to do here is this. There is a formula. The formula is percentage yield. Percentage yield is equals to the actual yield. Or what we call actual yield, or what we call actual yield or what we call experimental yield from our experiment. This is what we will get. Experimental yield, if you cannot understand it, divided by theoretical yield Another word for theoretical yield is the calculated yield. Calculated yield times 100. So in this case, we have been given the percentage yield. We have been given the percentage yield. We have been given the percentage yield, which is equivalent of which is 0.6. 0.6 is equals to the actual yield. Actual yield divided by what? Divided by the theoretical yield. Divided by the theoretical yield. The theoretical yield is what? Is 2.3. Is 2.3 gram. Remember that we are not going. This is the percentage that we have been given. We cannot use this again because the percentage, we have got the percentage. We have this because of this. So we will only have is 0.6 equals to the actual yield. Actual yield divided by 2.3. We are timesing it by 100 if we want to have the percentage. Now that the percentage has been given, we don't need to substitute it. We don't need 100 again, because we have already divided it by 100. So it is 0.6 equals to actual yield all over 2.3. Equals 2.3. And now, what would be our actual yield? Our actual yield will be equals to what? Will be equal to 0.6 times 0.6 times 2.3, which will be equals to 0.6 times 2.3, which will be equals to 1.38. 1.38 gram. 1.38 gram. The calculation, let me see the calculation. 0.6 times 2.3. Yeah, 1.38 gram. 1.38 gram. So it is 1.38 gram. This is the formula. I said this is the formula that we usually calculate percentage yield. This is the formula for percentage yield. To have your percentage yield, what you do is you would do actual yield divided by the theoretical yield times 100. But the percentage yield has been given. There's no need for 1,000. There's no need for 100 again. So you don't need to substitute the percentage yield because the actual yield all about this. Because I have already divided these by 100. I've already divided as 60% by 100, which I said 60% is equivalent to 0.6. So now our actual yield is 1.38 gram. If we go to our answer column to see if we can have 1.38 gram for question number 30, question number 30, we will have 1.38 gram will be B, and we say B is our right answer for question number 30. Question number 30, and the right answer is B, 1.38 gram. Now, question number 31. Question number 31. Question number 31. Which product gives a positive test with alkaline aqueous iodine and does not show optical isomerism? First, for a compound to give a positive test with alkaline aqueous iodine, that compound must have a methyl group that is attached to the carbon atom that has the functional group. Once more again, for it to give a positive test with alkaline aqueous iodine, we are talking of iodoform test, or we call it triiodomethane. Either we call it a triiodomethane test or iodoform test. This is the test. So for a compound to give a positive test with alkaline aqueous iodine, that compound must have a methyl group that is attached to the functional a methyl group that is attached to the carbon atom that has the functional group. Then again, for a compound to show optical isomerism, the compound must have a chiral carbon atom. A chiral carbon atom is a carbon atom that has 4 different functional groups. Let me just show you something here. For this purpose. Now, for it, I said for a compound to show optical activity, a positive test with or have a positive test with iodoform tests, to have iodoform test or show a positive test, what must happen is that it must have a methyl group. This is a methyl group that is attached to a carbon atom that has the functional group. And the functional group here is, we are talking of, this is the keto group. This one cannot go because this is an ethyl group. This is not a methyl group. This one cannot go. This one can go. C can go. C has a methyl group that is attached to a carbon atom that has a functional group. But the problem with it is that it has what? It has a chiral carbon atom. A chiral carbon atom is a carbon atom that has 4 different functional groups. And I mark all the carbon atoms with chiral carbon atom, carbon that have 4 different functional groups with asterisk. For example, this one, it has an aldehyde group, it has hydrogen, it has OH group, and it has an ethyl group. This is, it has optical activity. This one has an optical activity because it can show optical isomerism because it has 4 different functional groups. This one, it hasn't got any functional, it doesn't have any optical activity. There's no carbon atom there that has 4 different functional groups. C has a functional group. It has a carbon atom that has 4 different functional groups. So it has can undergo optical isomerism. D does not have a compound that does not have a carbon atom that has 4 different functional groups. Instead it has a carbon atom that has 2 methyl groups. So now let's analyze it. They said it must have a methyl. It must show a positive test with alkaline aqueous iodine. It must show a positive test. It must give a positive test with alkaline aqueous iodine, but should not show optical isomerism. So let's analyze our compound. So the first thing you do is draw the structures of the different compounds and analyze them. This one here, yes, it has a methyl group that is attached to a carbon atom that has a functional group. In that case, this one will give a positive test. It will give a positive test, but it has no optical property. There's no optical isomerism here. So this one might be the right answer. A might be the right answer. Let's go to B. B, it must have a methyl group. It has but an ethyl group. This is not a methyl group. So this one will not give a positive test with the alkaline aqueous iodine, because instead of a methyl group, this one has but an ethyl group. But it has an optical property, so it cannot even give a positive test. And again, it has an optical property because it has OH group, CHO, hydrogen, and the ethyl group. So the one gives a negative test but has optical property. It has also failed the test. So let's go to C. C will give a positive test because C has a methyl group attached to the carbon that has a functional group. But the one that has no optical activity, but C has an optical activity because C will give a positive test, and the C also has an optical property because it has a carbon atom that is attached to 4 different functional groups: OH, CH3, H, and this other group. All these, we consider it as a different group under the carbon. So C has failed. D, this would have been possible, but it has 2 methyl groups. It's not possible. So 2 methyl groups attached to the carbon atom having the functional group. That is not possible. And again, it has no optical property. So it is not possible. In that case, I said this one with the asterisk shows that it's a carbon atom having 4 different functional groups. So in that case, we will conclude that only A can give a positive test and has no optical activity. So A is our answer for question number 31. A is our answer for question number 31. A is our answer. Question number 31. A. Question number 31, A is our answer. Let's go to question number 32. Question number 32. Question number 32 will be question number 32. What is question number 32 telling us? Question number 32 is telling us that X and Y are the reagent required to convert one bromopropane into butanoic acid. Wow. Okay, one bromopropane. It has only 3 carbons. In that case, it will have to undergo an addition reaction, and that additional reaction will come from a reagent that will lead to addition of a carbon atom, and usually it is always a cyanide that is used for this purpose. In that case, there must be a cyanide, either potassium cyanide, that is there. Either potassium cyanide, because potassium cyanide is toxic. Remember, I told you potassium cyanide is toxic. Potassium cyanide must react with hydrochloric acid. Potassium cyanide must react with hydrochloric acid. When potassium cyanide reacts with hydrochloric acid, hydrogen cyanide is formed, because hydrochloric acid will provide the hydrogen and the potassium cyanide will provide the cyanide. So a hydrogen cyanide will form. It's the hydrogen cyanide that will provide the cyanide ion. The cyanide ion now will do what? Will attach itself to this compound. We'll call it nucleophilic substitution. The cyanide ion will be acting as a nucleophile. Will be acting as a nucleophile to attach itself here to substitute the bromide ion, because there will be what we call heterolytic fission. Bromine will go and the cyanide will attach itself here. And when cyanide attaches itself here, it will be CH3, CH2, CH2, and CN. In that case, we will obtain nitrile. It will be a nitrile. It will lead to a nitrile. That is CH3, CH3, CH2, CN. It will lead to a nitrile. This nitrile will undergo what we call acidic hydrolysis. Acid hydrolysis. The nitrile will undergo what we call acid hydrolysis. And in that acid hydrolysis, we will be converting. We will remove the nitrogen and add, but it will be zero. It will be COOH, leading to the acid. Acid hydrolysis. That is the acid in the water, and water now the OOH will come there. In that case, we have converted the halogenoalkane, which is bromopropane, one bromopropane, to what? To the corresponding acid through two steps. First of all, we'll convert bromopropane to 1, 2, 3 butane nitrile through the addition of a cyanide. That will through the addition of a cyanide, and that will be through nucleophilic substitution. The cyanide will be a nucleophile. Now there is an addition of one carbon here. This one carbon is the one that has given us now to butane. Now we need to undergo hydrolysis. It will be acid hydrolysis. The sulfuric acid, dilute sulfuric acid, and this will now be converted to what? To the corresponding acid, which will be butanoic acid. 1, 2, 3, 4 with butanoic acid. So in this case, the reagent X is what? The reagent X will be potassium cyanide, potassium cyanide in ethanol, or you can call it ethanolic potassium cyanide. So it is potassium cyanide in ethanol, and what? An acid hydrolysis, which will be Y. The acid hydrolysis, that is the acid in water, then that will do this to convert this the nitrile, the butane nitrile to what? To butanoic acid. So it will be acid nitrile. So in that case, it is leading us that our right answer here is C. Our right answer here is C. Our right answer here is C. So 32, our right answer is C. We are not going to use, remember, do not be confused with, if we were to use sodium hydroxide, that's when we can lead to alcohol. May lead to alcohol. But acid hydrolysis is the one that is leading us to butanoic acid. Remember this. We are using but acid hydrolysis, not alkaline hydrolysis, please. Acid hydrolysis will lead us to butanoic acid once more. Okay, question number So our right answer is C. Question number 33. Question number 33. Question number 33. We have question number 33 to be, which mixture could be used to produce propyl methanoate? Propyl methanoate. This is an ester. Propyl, then methanoate. Propyl is telling you that this alkyl group here is coming from alcohol, because when we start naming esters, we start but from the group that comes from the alcohol and end with the group that comes from the acids. So propyl methanoate means that it is the formation of esters when a carboxylic acid reacts with an alcohol. When a carboxylic acid reacts with an alcohol, an ester is formed. So it is that group of the alcohol that we start naming it with. So if it is propyl, that means the alcohol was propanol or propan-1-ol. The alcohol was propanol or propan-1-ol. If it is a methanoate that we are ending it with acid, then the acid was what? Was methanoic acid. Let's see if we can write the answer, the equation here. Now this is propan-1-ol and this is methanoic acid. So when an ester is formed by condensation reaction, a molecule of water is taken away. So a molecule of water is taken, and we would all call this propyl methanoate. I said once more, we start naming the ester using the alkyl group from the alcohol. So from the alcohol, the alkyl group is propyl, and they will end with the one from the acid. So we now call it propyl methanoate. So this is how the formula is supposed to be: propyl methanoate. And propyl methanoate, we use propyl methanoate, that is question number 32. Propyl methanoate, this is our formula here. Propyl methanoate, we will have, so we are looking from propan-1-ol and methanoic acid. So our answer for question number 33 will be B, because we are from propan-1-ol and methanoic acid. It's methanoic acid, not this, methanoic acid. So we are reacting propan-1-ol and methanoic acid. This is propan-1-ol, 1, 2, 3, and this is a methanoic acid. So we are on the right answer, B. Okay, let's go to question number 34. Let's go to question number 34. Question number 34 is question number 34. Question number 34 gives us a certain thing, and they tell us which series shows molecules in order of increasing bond angle. Methane to trifluoro, that is what? Boron trifluoride. That's good. From methane to boron trifluoride, then to ammonia. Okay, I just drew something here. You look at it here, right? That from here you will see that from methane has a bond angle. Methane has a bond angle of 109. Let's see, ammonia has a bond angle of 107. Boron trifluoride has a bond angle of 120. Carbon dioxide has a bond angle of 180. And water has a bond angle of 104.5. Okay, methane has a bond angle of 109, 109.5. Water has a bond angle of 104.5. Ammonia has 107. Ammonia has 107. Our question says, which series shows molecules in order of increasing bond angle? Increasing bond angle, A is already out because it is starting from 109 and ending at 7. So it is off. So B, B which is 104, carbon dioxide is 180, carbon dioxide is 180, so it has gone right up, then fall again. It doesn't work. Then C is 107, methane is 109. That's good. 107 to 109. Then carbon dioxide is 180. Carbon dioxide is 180. Carbon dioxide is 180. So C is increasing from 107 to 109, and then from 109 to 180. That's good for C. Then D, 107. Methane is 109. Then water again 104. It doesn't work. So C is likely going to be our right answer. And if you analyze it here like this, from ammonia to methane, that is C, and then to carbon dioxide. Ammonia is 107. This is C. Ammonia, methane is 109.5. Carbon dioxide 180. Now, what is causing this shape like this? Because it has one lone pair of electron here. That is what is giving ammonia this thing. There is repulsion, and it has one lone pair of electron. And how many bonding electrons are there? How many bonding pairs of electrons? We have 3 hydrogen. So there's a bond here, there's a bond here, there's a bond here. So one lone pair of electron, 3 bonding pair. And this lone pair of electrons is the one that's causing a repulsion here, and that result in a pyramidal shape. For the purpose of revision again, for methane, it has 109.5. Why? It has 4 different bond pairs. 4 different bond pairs. Then, for that reason, of that 4 different bond pair, it has a shape of, it has a tetrahedral shape. For the purpose of revision, once more, carbon dioxide, it has this type of shape. It has 2 lone double bonds on each side. With oxygen, you have something like this, something like that, and that gives carbon dioxide a linear shape. And since it is a straight line, something like that, it's a straight line. So what we'll say, the angle will be what? Will be 180. So that is why it says the angle here is increasing from 107, 19, and to 107, 109 to 180. So this answer is right. Number 34, that describes, number 34, that gives us from ammonia to methane and to carbon dioxide, is the one that we say it is the right answer. So C is our right answer for this. C is our right answer. Question number 35. Question number 35. We will have something like this. The reaction ethanol, this ethanol, it's an aldehyde, plus hydrogen cyanide will give what? Will give 1, 2, we'll call it, this is 1, 2, 3. We'll call it 2-hydroxyl propane nitrile. It is 2-hydroxyl propane nitrile because this is the first carbon, this is the first carbon, this is the second carbon, and this is the third carbon. And the OH group is located on what? On the second carbon. And The nitrile is the one that is an addition reaction, because there were two carbon atoms here, and the cyanide that comes in, will add on this carbon here, giving us an additional carbon atom. It's the cyanide that has brought an increase in the number of carbon atoms. So it is it's a nucleophilic addition, because the cyanide will come in as a nucleophile when hydrogen dissociates. Okay, when hydrogen sulfide, hydrogen cyanide goes in solution, is going to have this plus a cyanide ion, and this compound, as we see this compound like this, it is this that will have this. We have this propane nitrile. This is going to come in as a nucleophile. This will be a nucleophile here. Here, there's going to be it's going to be like a nucleophile in this reaction here. This will be a nucleophile. Nucleophiles are they are electron pair donor. They are going to donate an electron here. So this one, this lone pair is going to be shifted in here. The lone pair is going to be shifted in here. The lone pair is going to be shifted in here. And when the lone pair is shifted in here, what happens? There's going to be a cyanide. This one is going to be, there will be a cyanide here. Okay. The lone pair here does what? There's a lone pair here. Let me just say there's a lone pair here. Moment. So you see here. So when this will lead to what? This is a nucleophile here. Nucleophiles are electron pair donors, so they are going to donate the lone pair here. So when it comes here, there will be a positive charge and a negative charge here. So that is the mechanism here. So that is what will happen. We will have this compound here. Yeah, CH3. Oh, sorry, please. It is what we say. It was ethanol. Sorry, it was ethanol. Please. So now, so what happens here? This is it. The one comes here, and this will be here. The cyanide will be here now. The cyanide over here. Then this hydrogen that was in solution will pick this one will be picked by the hydrogen in solution, resulting in what? Resulting in this H. We'll pick the hydrogen in solution and resulting in this. And when it results, that's why we now say it is 2-hydroxyl propane nitrile. So that is just the mechanism I just gave you. So we now say that this is nucleophilic addition. You are adding a nucleophile onto this compound. Let's go back to our question now and see what is the answer that matches that one. Okay, this reaction is an example of this nucleophilic electrophilic substitution. No. Nucleophilic addition, excellent. I don't need to be going ahead again. 35 is B. Free radical, no. No, it is nucleophilic addition. I've just shown you the mechanism there. So that is what happens. So our answer for this, question number 35, is B. Is B. Question number 36. We need to find time. Question number 36. For question number 36, we will have question number 36. What is the accepted conventional name for the compound, for this compound? What you need to do is you need to draw down the compound. Let me draw down the compound for you. That is the compound that we have that I've drawn here. We have drawn the compound. That is the compound that was given. I've drawn it now. Let's see how we can name the compound. In naming the compound, according to the IUPAC, that is International Union of Physical and Applied Chemistry, what we need to do is we know the longest chain is the one that we are going to do it, and we start numbering where the branching start. We will start naming where the branching start. The branching start here. Okay. The longest chain is 1, 2, 3, 4. Okay, we can start numbering from here again. We can number like this. 1. We can number this one. 1, 2, 3, 4. It's the same thing. It is still on the 2 position. If we number that 1, 2, and the 3 here, this is the shortest chain. It's not necessary. We are taking by the longest chain. So if we go round like this, we will still come to the same thing. If we go straight the same thing, we'll come to the same thing. Therefore, 2 is going to be our position. That's going to be our position. And now the side chain here, the alkyl group here is what we call the methyl group. The methyl group. So we now say it is 2 dimethyl. Then how many carbon atoms are there? 1, 2, 3, 4. So 2 dimethyl butane. And let's see if that is our answer. Okay, 2 dimethyl butane. In that case, we say A is our answer. We don't need to be going ahead. Now, let's go to question number 37. Question number 37. Question number 37 has to do with equation. Which equation has an enthalpy change of a reaction which correspond to the standard enthalpy change of atomization? We are atomizing it must be from a gaseous atom, from a gaseous atom to from a gaseous molecule like that to a gaseous atom. So in that case, it must be gaseous. We don't need to do with this one. So A, I would have said A is the. Let me first say yeah. B, no. This one no. This one no. So atomization is A. Atomization is A. A is our right answer for atomization. So A is our right answer. So if we were to do this, A is our right answer. So A is our right answer for this. Okay. A is our right answer for question number 37. Question number 38. Question number 38 to 45 has to do with some other things again. They have said, okay, when question answers A, 1, 2, and 3 will mark A, 1 and 2 is B, 2 and 3 is C, and if the answer is only 3, we have a D. Question number 38. Let's go straight. Two solutions of aqueous hydrochloric acid were put into 2 different beakers, 1 and 2. Two solutions of hydrochloric acid were put into 2 different beakers, 1 and 2, respectively. 2 different samples of magnesium were added to each of the beakers, and the rate of production of hydrogen gas was measured. It was observed that the rate of the reaction in beaker 2 was greater than the rate of reaction in beaker 1. What is the likely explanation of this observation? Of course, it was dilute hydrochloric acid in the 2 containers, in the 2 beakers. Then we can bring magnesium ribbon into the 2. When we put magnesium ribbon of the same mass into the 2, if there's a change in any reaction, there's one thing: either the concentration of the acid has changed or has increased. Where the rate of reaction increases, it means the concentration in that test tube the concentration of the dilute acid in that test tube was higher. So in that case, let's see our answers. It means that the reaction in beaker 1 has a higher activation energy. No, the magnesium in beaker 1 is in larger piece than the one in the that's not the case. That's not the case. The larger piece is not the one. It's not the larger piece that causes the rate of reaction. Instead, it is it's not the larger piece that causes the rate of reaction. It instead is the surface area. The larger the surface area, and only smaller particles will have larger surface area. So that one is totally wrong. The acid the acid, so the larger piece here is not will instead slow the reaction. So 3, the acid in beaker 2 is at a higher concentration than the acid in beaker 1. That's the only answer, because 1 does not tally with rate of reaction, 2 does not tally with rate of reaction. So it's only 3 that is tallying with the rate of reaction. So the only answer is 3, and 3 is what? Is D. I will say it is D here. So question number 38, the answer is D. Question number 39. Question number 39. Question number 39. Question number 39. Which one of the following statements are correct? Which one of the following statements are correct for an atom? Which one for an atom? Atoms of all elements contain protons, neutrons, and electrons. You need to know atomic structure. The atom is composed of what? Okay, atoms of all elements contain proton, neutron, and electron. That is wonderful. 2, an atom is electrically neutral because it contains equal number of electron and equal number of electron and number of proton. That is also right. The ionization energy of an atom is a direct measure of the ease with which an atom can lose an electron. So now you see that question number 1 is right. Question number 1 is right. Our answer is question number 1 is right. Question number 1 is right. That according to the atomic structure, an atom contains the proton, neutron, and electrons. 1 is right. For an atom to be neutral, the number of electrons must be equal to the number of protons. That is right, because protons are positively charged, electrons are negatively charged, so they must be equal to cancel each other. When the number of neutrons are higher than electrons, that is when an atom has a charge, a positive charge. When the number of electrons are higher than the number of protons, that's when an atom has a negative charge. If an atom is neutral, that means proton and electron are equal and they cancel out each other. So 2 is right. 3, the ease with which an atom can lose an electron. Yeah. So the right answer for this, for question number 39, is 1, 2, and 3. And 1, 2, and 3 is what? A. So 39 is A. Question 39, the answer is A. Question 39, the answer is A. Then question number 40. Question number 40. Which statement about reversible reaction are correct? Which statement about reversible reaction are correct? An increase in the concentration of a reactant always increase the concentration of the product. Of course, For a reversible, when you increase the reactant, the other one will also increase. So it's reversible. 2. An increase in the temperature always increase the rate at which equilibrium is established. Yes, equilibrium is established when there's an increase in temperature. So if you look at it, then addition of catalyst will increase concentration. No, 3 is not really right. The right answer for this is 1 under 2, and which is B. The answer is B. Question number 41. Question number 41. The halogenoalkane listed below all react with sodium hydroxide. Which compound proceed mainly by SN1 mechanism? An SN1 mechanism, which we call a nucleophilic substitution unimolecular. That is, only one reagent is involved in the rate determining step. In this type of reaction, we have 1 iodopropane. We have 2 methyl propane. And we have 2 bromo, 2 methyl butane. Here we need to know which one is a secondary and which one is a primary, secondary, and tertiary halogenoalkanes. Because only tertiary and secondary halogenoalkanes will undergo SN1 mechanism. Once more, note, only tertiary and secondary halogenoalkanes will undergo SN1 mechanism. No primary. No primary. Only tertiary and secondary. So we need to know, draw the structures of these, the structures of the halogenoalkanes, and to see which one is a primary, a secondary, and tertiary. Then we will select only the tertiary and the secondary, because these are the only ones that will undergo SN1 mechanism. In drawing this structure, the first one which is 1 iodopropane. This is 1 iodopropane. This is 1 iodopropane. That is the first one. Then the second one, which is 2 bromo, 2 methyl butane, 2 bromo. It is 1, 2, 3. So it is 2 bromo. The second one. Which one is this? Is first iodo. That is 1 iodopropane. So this one is 2 bromo. This one is 2 bromo, 2 bromo, 2 bromo. Let me see this one. Yes. Two bromo, 2 bromo, 2 methyl butane. So 2 bromo, yes. Yeah. Yeah. So this is 2 bromo, 2 bromo, 2 methyl propane. So if we are to number the structures, this is how the numbering is. This is the first carbon atom, this is the second carbon atom, this is the third carbon atom, and this is the fourth carbon atom. We can see say this is the first carbon atom, and this is the second carbon atom in that order. On the second carbon atom, we have bromine there. That's why we say 2 bromo. Then on the second carbon atom again, we are following this one. we are following this one, 1, 2, 3. On the second carbon atom we have bromine, and on the second carbon atom we have a methane. That's why we say 2 bromo, 2 bromo, 2 bromo, 2 methyl, then 1, 2, 3, 4, 2 methyl butane. That is for number 3. Then this one, so this is for number 3. Now and this one is here. This is still a tertiary halogen alkane. This is still a tertiary halogen alkane. It is a tertiary halogen alkane. This is a tertiary halogen alkane. Now let's go to that one. The other one is 2 iodo 2 methyl propane. Yes, we want to number it just the same way of the IUPAC system of nomenclature. We have 1, we have 2, we have 3. That is number 2. That is 2 iodo 2 methyl propane. Or you can still number it from here. So it is 1, 2, 3. On the second carbon atom we have iodine. That's why we say 2 iodo. On the second carbon atom we have a methyl group, 2 iodo 2 methyl, 2 methyl. And how many carbon atoms are there? 1, 2, 3. So 2 iodo 2 methyl what? Propane. It's the same thing like this one here, but the only thing is that this one is propane, and while this one is butane. Number three is butane, and number 2 is propane. So this is a tertiary halogen alkane. This is a tertiary halogen alkane. This is a tertiary halogen alkane. This is also a tertiary halogen alkane. So we said that only tertiary and secondary halogen alkanes will undergo SN1 mechanism. And in this our reaction here, we don't have any secondary, so only the tertiary are there. The rule is only tertiary and the secondary will undergo SN1 mechanism. But in this case, we don't have any secondary here. We have only 2 tertiary and 1 primary. So primary is not involved. In this case, we will have 2 and 3. 2 and 3. 2 and 3. Reaction that involve 2 and 3 are what? Reaction that 2 and 3 will undergo that. See? 2 bromo 2 methyl butane. Okay. Yes. Methyl. This is a tertiary halogen alkane. 3 is a tertiary halogen alkane. Here, 2 iodo, 2 methyl propane. One, two, three. Still a tertiary halogen alkane. So in that case, so we will have 2 that will have to undergo it. So now we will have question C, whether we undergo 2-bromo 2-methyl butane, which is 3. A, B, C, D. So which is what is the answer column? To 45. We have 2 and 3. 2 and 3 are all tertiary halogenalkanes. This will undergo SN1. This will undergo SN1. 2 and 3 will undergo SN1. This and this will undergo SN1. That will undergo SN1. And if we have to undergo SN1, then our answer here will be what? Our answer here will be our answer 2 and 3. Our answer will be C. Our answer will be C. Our answer for 41 will be C. So our answer will be C, because it is only 2-iodo 2-methylpropane. Only 2-iodo 2-methylpropane. 2-iodo 2-methylpropane and 2-bromo 2-methylbutane. These are tertiary halogenalkanes, and we said only tertiary and secondary halogenalkane will undergo SN1. In this case, we don't have any secondary halogenalkane. So the only one that will undergo SN1 mechanism are the tertiary halogenalkanes. And the tertiary halogenalkanes here in this question are 2 and 3. And 2 and 3 will give us the answer, which will be C. So the most essential thing here is you should know which type of halogenalkane that will undergo SN1 or SN2. Is it primary, is it secondary, or is it tertiary? Then the next hint here is that you need to draw the structures, identify which one is a primary, identify which one is a secondary, and identify which one is a tertiary. From there, you now select your right answer. Let's go to the next question, question number 42. Question number 42, which is question number 42. Question number 42. Question number 42. Question number 42 is which property increased from magnesium to barium? 42. Which from magnesium to barium? Which property increased from magnesium to barium? So the property that will increase from magnesium to barium will increase. That's 42. Ionic radius of magnesium. Which property increased from magnesium to barium? As you go down the group, the ionic radius of magnesium. The ionic radius, yes, it will depend. As you go down the group, they have the same charge which is +2, but the atomic size is, the ionic size is decreasing. So many other shells are being added. 2, screening of outer electrons by the inner electron. This is what we call the shielding effect. That is the protection of the inner electrons from the protection of the outer electrons from the attraction of the nucleus. The shielding effect. Of course, it is as you go down the group, many more shells are being added. So there is the atom become larger. For that purpose, the inner electrons are being shielded. The outer electrons are being shielded from the attraction of the nucleus by the inner shells. You are right, and that increases down the group. Solubility of hydroxide. Of course, the hydroxides are decreased. The solubility of the hydroxide are decreasing down the group, making magnesium hydroxide even insoluble. Magnesium hydroxide to an extent is really insoluble in water. So, but as you go down the group to barium, the solubility increases. So 1, 2, and 3, they are all right when it has to do with from magnesium to barium. All the properties are right. They increase as you go down the group. So 1, 2, and 3 are right. And 1, 2, and 3, which answer is that? 1, 2, and 3. 1, 2, and is A. 1, 2, and 3 is A. So we will say A is our right answer here. Okay. Question number 43. Question number 43. The melting point. The melting point. The melting point of chlorine is lower than the melting point of iodine. Which statement helps to explain this difference? One will tell us that what makes chlorine the melting point of chlorine to be lower than that of iodine. In this case, intermolecular forces is going to play a very big role. Increase in the molecular weight, increase in the number of electrons, increase in the instantaneous dipole-induced dipole attraction. So as you go down the group, the number of electrons are increasing, increase in the instantaneous dipole-induced dipole attraction. And the energy that is required to overcome them will be higher, leading to what? Leading to what? An increase in the boiling point, in the melting point. So let's see our answer. The covalent bonds between the atoms stronger? No. I say it has to do with intermolecular forces, which I have just explained. 2. Iodine molecule is more polar? No. 3. Iodine has more electrons than chlorine, and so has stronger van der Waals forces. Excellent. So the answer is 3. And if the answer is only 3, then the answer is D. 43 is D. 43 is D. 44. The Bronsted-Lowry theory. The Bronsted-Lowry theory of acid-base behavior. Water can behave both as acid and base. Water can behave both as acid and base. Yes. The conjugate base of HSO4 is SO2 minus. Okay. For your understanding, please, let me just brief you on this before we come to the answer for the purpose of revision. You should know that every acid has a conjugate base, and every base has a conjugate acid. Once more, every acid has a conjugate base, and every base has a conjugate acid. What is a conjugate base? What is a conjugate base? That is the main important thing. Don't only look at the equation. What is a conjugate base? The simple explanation of a conjugate base is that a conjugate base, this is the particle that is left, or this is the substance that is left after the acid has given away its proton. When the acid donates a proton, what is left is what we call a conjugate base. For instance, water is acting as an acid. Water is acting as an acid. Now, if water donates a proton, now I said acid, a conjugate base. A conjugate base is that substance or is that particle that is left after the acid has donated or has given away its proton. For example, water acts as an acid. If water loses or donates its proton, because acids are proton donor. acids are proton donors. So the conjugate base is that substance that is left after the acid has given away or has donated its proton. Since water acts as an acid, immediately it gives away its proton. What is left is the conjugate base. Then again, what is a conjugate acid? A conjugate acid is that substance or that particle that is formed. That particle that is formed when the base has accepted a proton. When the base has accepted a proton, the substance that is formed is the conjugate acid. For instance, this is a reversible reaction. This is a reversible reaction. This is the conjugate base, and this is what? This is the conjugate acid. This is the conjugate acid. I say it is that substance. The conjugate acid is that substance that is formed. Is that substance that is formed when the base has accepted a proton. This is the base. If this is the base and the base has accepted a proton, then this is the conjugate acid. In other words, let's say a base is ammonia. And if ammonia accepts a proton, what will be our conjugate acid? I said the conjugate acid is the particle formed when the base has accepted a proton. What is a proton? Remember that a base is a proton acceptor. Bases are proton acceptors. So when the base accepts a proton and form a substance, the substance here will be what? NH4. And this is what we call the conjugate acids. That is the conjugate acid. So going back to our answers. Going back to our answers here. Going back to our answer here. Going back to our answers there. We are here. Where we are. Okay. Water can behave as both acid and base. Good. I've just illustrated it there. 2. The conjugate base for this. The conjugate base for this is this. When the conjugate base of this is this one. The conjugate base for this is this. The conjugate acid of ammonia is this one. It's a lie. So the conjugate base, I said the conjugate base, the base is the substance left after the acid has given away its proton. If this gives away a proton, if this HSO4 gives away its proton, if this one gives away its proton, what the substance that will be left is this one. So the conjugate base of this substance here, if it gives away its proton, this is what will be formed. And if this one accepts a proton here, this is what will be formed. So if we take away hydrogen from here, this is what will be there. And there will be an additional this thing there. So in that case, 1 and 2 are the right answers. And 1 and 2 being the right answer, our answer will be what? Our answer for question number 44 will be B. Our answer for question number 44 will be B. That's just all. Question number 45. Question number 45. Question number 45. Which of the following processes are likely to be exothermic? Exothermic, when heat is being released to the surrounding. Here, this is the first electron affinity. The first electron affinity is The first electron affinity is exothermic. The first electron affinity is exothermic. It is the second electron affinity that is endothermic, because more heat is needed to add the second electron to the first. So the first one is exothermic. Which of the following processes are likely to be? The first one is exothermic, good. The second one, combustion of magnesium ribbon. If we combust magnesium ribbon, what is observed is that heat is being released to the surrounding. If you go to the laboratory, you take magnesium ribbon and you place it under the Bunsen burner, you will see how there is a lot of heat that is being generated. And when heat is being released, we call that an exothermic reaction. For that purpose, this one is also exothermic. Then sodium in water. You know how sodium reacts. Reaction of sodium with water. Sodium ionic water. Sodium reacts explosively with water. It reacts violently with water. Sodium, group 1 metals, they react violently with water, especially sodium and the potassium. That is why sodium is stored under paraffin, because it reacts violently with water. So, when it reacts violently with water, energy is being released. Heat is being released to the surrounding. So that is an exothermic reaction. This is also exothermic. So 1, 2, 3 are exothermic reaction. And if 1, 2, 3 are all exothermic reaction, if 1, 2, 3 are all exothermic reaction, so our answer, that is our answer for question number 45. Our answer for question number 45 will be A. Our question for question number 40. Our answer for question number 45 will be A. Thank you, learners, for listening. Thank you. It's a great pleasure. Thank you. Once more, I want to remind most of you who haven't subscribed to our channel. I want to remind most of you who haven't subscribed to our channel, please, as I told you, we are not asking you to donate or to buy pamphlets. Our resources are free for you people to use. And our main goal is that you succeed in your studies. Therefore, what we want from you is subscribe to our channel, like our videos, and share to other fellow learners. Thank you, thank you, thank you, thank you, thank you, thank you for that. Thank you for that. Thank you for your collaboration.